In my last lecture on the determination of crystal structure of a material by X-ray diffraction, I had mentioned that due to errors in measuring the length between a line pair in the diffraction pattern, we commit some errors in the calculated value of theta, sin square theta, etc. These errors ultimately get reflected in the measured, or rather in the calculated values of the interplanar distances d, and also in the value of the lattice parameter or parameters of the material. I had suggested that the most accurate value of lattice parameter or parameters could be obtained by considering the highest angle line in the diffraction pattern. Today, I am going to explain why I said so. At the same time, I shall also describe the procedure of calculating the lattice parameter or parameters very precisely following some method. Now, to start with, I would like to show a plot of sin theta versus theta. So, this is the plot of sin theta versus theta. Now, say while measuring the distance between the line pairs for a particular diffraction line, we commit some error, and that error will cause an error in the calculated value of theta. Say for example, this much is the error in the calculated value of theta. That means, this is the value which is the actual theta minus the measured theta. How much change this error will bring in the calculated value of sin theta? We can see that this much is the change in sin theta, which will be caused by a change this much in the calculated value of theta. Now, if we commit the same mistake for a higher angle line, say over here, that means this is the amount of error which is equal to this, and then if we figure out what will be the corresponding error in the sin theta value, it will be only this much. So, we see that the same amount of error in measuring theta at the low angle side and at the high angle side in a diffraction pattern, they will produce different amounts of error in the sin theta value. Not only that, the error for the higher angle line will be much less as compared to the error for a low angle line. And this is the reason why when we have a diffraction pattern and when we are asked to calculate d and therefore A, the lattice parameter, we always choose a high angle line. But choosing a high angle line is simply not enough. There are several sources of error for the lines obtained on a Debye-Scherrer pattern, and these errors are: number 1, shrinkage of the film during processing and drying; number 2, incorrectly measured camera radius; number 3, off centering of the specimen; and fourthly and finally, absorption of X-rays by the specimen. So, these are the causes for the errors which we commit in the measurement of line distances in a diffraction pattern. Let us consider the errors due to shrinkage and incorrect camera radius together. Say for example, we concentrate on a high angle line in the back reflection region of a Debye-Scherrer camera. So, this is the direction of the incident X-ray, and suppose from a particular atomic plane we find the diffracted beam intercepts on the film at y y. Now, this angle 2 theta is the angle between the incident direction and the diffraction direction. Let us suppose that this angle here is 2 phi, which is 180 degree minus 2 theta. Now, when the film is developed and dried and we make a measurement on this particular line pair, say the distance we measure as S prime. Therefore, we can write down phi, or rather 4 phi into r will be equal to 4 phi divided by S prime will be equal to 360 degree divided by pi d, where d is the camera distance. But straight away we can write that phi is equal to S prime by 4 r, where r is the camera radius and S dash is the distance between the line pair in question. So, we can write down phi is equal to S prime by 4 r. This equation can be written in logarithmic form as ln phi is equal to ln S prime minus ln 4 minus ln r. Differentiating this, we get delta phi by phi equal to delta S dash by S dash minus delta r by r, where what is delta S dash or delta S prime? This is the error in the measured value of S prime or S dash. And what is delta r? This is the error in the measured value of r. That means, if the camera radius is not measured very accurately. Therefore, the error in phi due to both film shrinkage and incorrectly measured camera radius can be written as, from this equation 3, delta phi 1, the error due to these two reasons, will be equal to phi times delta S prime by S prime minus delta r by r. So, from this equation we can find out delta phi as phi into this quantity. So, if this delta phi we refer to as the error in phi due to both film shrinkage and incorrectly measured camera radius, and designate it as delta phi 1, it will be simply equal to phi multiplied by delta s prime by s prime minus delta r by r. Now, we will find out how much the error is going to be due to the off centering of the specimen in the horizontal direction. Say for example, let C prime is the center of the camera. If the specimen is off centered, then its displacement from the center can be resolved into two components, a horizontal component delta x and a vertical component delta y. We will first discuss the off centering in the horizontal direction. So, if there is off centering of the specimen in the horizontal direction, then instead of being at the correct center of the camera C prime, the specimen is displaced along the horizontal direction to a point P. So, this distance over here is equal to delta x, say. If we put a perpendicular from P on this line, then it is P n, and this length will be equal to delta x sin 2 phi. Now, due to diffraction, the sample, the diffraction of the specimen at the point P, these will be the diffracted beams, namely P d and P c, which will intercept on the film at the points C and D. But in fact, the specimen should have been at C prime, the actual center of the camera, and in that case C dash B and C dash A would have been the correct positions of the diffracted beams on the film. So, the actual measured distance for the diffracted beam for the line pair coming out of this sample should have been S prime, but there is an error because of off centering, and for that reason we are measuring a distance only C d. Now, the total error in the measured value of S prime due to displacement of the specimen in the horizontal direction will simply be A c plus d b, but A c and d b will be practically the same, and d b can be taken to be equal to P n, where P n is a perpendicular to the line C dash B. So, we can write the total error in the measured value of S prime only for horizontal displacement of the specimen will be equal to A c plus d b, which is equal to twice d b, equal to 2 times P n. But how much is P n? P n is equal to delta x sin 2 phi. So, P n is delta x sin 2 phi. Therefore, if S prime h is the error in S prime due to the horizontal displacement of the specimen from the center, then S prime h can be written as 2 times delta x sine 2 phi. Now, if we consider the error due to off centering of the specimen in the vertical direction, the appropriate diagram is shown here. You see, if the specimen were at C prime, the exact center of the camera, the diffracted beams would have struck the film at the point B and the point A. So, this should have been the correct value of S prime, but due to the vertical displacement of the specimen, whereby the specimen is placed not at C prime, but at P due to error, the diffracted radiations will intercept the film along PD and AC. Effectively, if the value of delta y is very small, then what will happen? We will have a situation where AC and dB can be considered very small, and as a result we can take AB is equal to CD is equal to S prime. Thus, the error delta S prime V for vertical displacement of the specimen from the center can be totally neglected. So, we can write delta S prime V, the error in the measured value of S prime due to the vertical displacement of the specimen from the center of the camera will be equal to 0. So, now what will be the total error due to off centering of the specimen? The total error in the measured value of S prime, which you can write as delta S prime, it will have two components. One is the error due to the horizontal displacement of the specimen from the center, which can be written as delta S prime h, and the error due to the vertical displacement, which is 0. However, we know that delta S prime h is equal to 2 delta x sine 2 phi. Therefore, the total error delta S prime due to the off centering of the specimen is simply equal to 2 delta x sine 2 phi. Now, if we consider that there is no error in the measurement of r, the radius of the camera, then the equation 3, which is delta phi by phi is equal to delta S prime by S prime minus delta r by r, will reduce to delta phi by phi equal to delta S prime by S prime. We have assumed that there is no error in the measured value of r. So, now the error due to the off centering of the specimen, which we can write as delta phi 2, can be written as delta phi 2 is equal to phi multiplied by delta S prime by S prime. So, this is obtained from this, and that will be equal to phi multiplied by 2 delta x sine 2 phi, which is the value of delta S prime, divided by S prime. Now, the equation 1 already shows that phi is equal to S prime by 4 r. Therefore, S prime is equal to 4 r phi. Now, if we substitute the value of S prime in equation 7 over here, we can write delta phi 2 equal to phi into 2 delta x sin 2 phi, and instead of S prime we write 4 r phi. That gives us a value of delta x into sin phi cosine phi divided by r. Now, we look at the error which creeps in due to the absorption of X-rays by the specimen. Say for example, this is the cross section of the specimen, say, and it is correctly mounted at the center of the camera. Now, if the specimen is made up of a material which is highly absorbing, then it will be difficult for the X-rays to penetrate the thickness fully. Naturally, the error produced in the measured value of S prime will be quite similar to that of the off centering of the specimen in the horizontal direction. You see, if this specimen, this is the cross section of the specimen is lying perpendicular to this plane. Now, if it is made up of a highly absorbing material, then the incident X-ray will find it very difficult to penetrate. So, as a result, instead of the diffracted beam coming from the center, you will find the diffracted beam will emanate from a point away from the center. So, the correct S prime should have been the length between A and B, but because of the highly absorbing material, we will find that the diffracted beam will be coming along in this manner, so that CD will be erroneously measured as the value of S prime. Now, this error due to the highly absorbing nature of the specimen is very similar to the error due to off centering of the specimen in a horizontal direction. So, we do not consider the error due to the absorption of X-rays by the specimen separately, since it has already been taken care of in the error due to off centering of the specimen in the horizontal direction. Now, what is the total error in the measured value of S prime? Now, we have already seen sigma phi 1 is equal to the delta phi 1 is equal to phi multiplied by delta S prime by S prime minus delta R by R. So, this is the error in the measured value of S prime due to both shrinkage problem and incorrectly measured camera radius. Similarly, delta phi 2, which is due to the off centering of the specimen plus the absorption by the specimen, is simply equal to phi into 2 delta x sin 2 phi by r 4 r phi. So, it is equal to delta x sin phi cosine phi by r. So, now the total error is given by combining these two equations. So, we will have error in the measured value of phi is equal to phi delta s prime by s prime minus 4r minus delta r by r plus delta x sin phi cosine phi by r. We have already seen from the previous diagram that 2 phi effectively is 180 degree minus 2 theta, where 2 theta is the angle between the incident X-ray direction and the direction of the diffracted X radiation. So, phi will be equal to 90 degree minus theta. So, in that case we can immediately write that delta phi will be equal to minus delta theta, sin phi will be equal to cosine theta, and cosine phi will be equal to sin theta because of this relationship. Now, we already know that for an XRD pattern of a cubic material taken with a Debye-Scherrer camera, we can write delta A by A, that means error in the measurement of lattice parameter, is equal to delta D by D, error in the measurement of D, the interplanar distance, is equal to minus cotangent theta delta theta. So, this will be equal to minus cosine theta by sin theta delta theta, or will be equal to sin phi by cosine phi into delta phi. If we substitute the value of delta phi from equation 9 here in the equation 10, we will get delta A by A will be equal to sin phi by cosine phi multiplied by phi into delta s prime by s prime minus delta r by r plus delta x sin phi cosine phi bar by r. For a high angle line, phi will be rather small and therefore can be replaced by the quantity sin phi cosine phi, since sin phi, when phi is very very small, can be written as almost equal to phi, cosine phi will almost equal to 1. Therefore, equation 11 can be rewritten as delta A by A is equal to delta s prime by s prime minus delta r by r plus delta x by r, the whole multiplied by sin square phi. Now, if we look at all the lines on an X-ray diffraction film, the bracketed term in this equation is a constant for all the lines in the pattern, and we can write it as the constant k, say. Therefore, the equation 12 can be rewritten as delta A by A is equal to k times sin square phi, or it will be equal to k times cosine square theta. Now, we can determine the lattice parameter quite precisely from by following this procedure. Say, let AC, A subscript C, be the value of the precise lattice parameter, and A subscript M be the measured value of the lattice parameter from any line in the XRD pattern. So, AC is a precise lattice parameter and AM are the measured values of lattice parameter from the lines in the XRD pattern. So, what will be the error delta A in the measurement of lattice parameter, it will be given by delta A is equal to AC, the correct value of the lattice parameter, minus the measured value written as AM. Therefore, the fractional error in the measurement of A is given by delta A by AC is equal to AC minus AM divided by AC. But we know that the equation 13 is already shown that delta A by A is equal to k cosine square theta. Therefore, we can write AC minus AM by AC is equal to k cosine square theta, or dividing both the terms by AC, 1 minus AM by AC is equal to k cosine square theta. In other words, AM by AC will be equal to 1 minus k cosine square theta, or we can write AM is equal to AC minus AC k cosine square theta, or we can write it as AM is equal to minus AC k cosine square theta plus AC. Since AC is a constant, it is the precise lattice parameter of the material, the term AC k is also a constant. That means, AC is a constant quantity, the actual lattice parameter, the precise lattice parameter, k is a constant. So, the quantity ACK is also a constant, say we write it as K1. So, this quantity ACK is now a constant and we can write it as K1. Therefore, this equation can be written as AM is equal to K1 cosine square theta plus AC. Now, this equation is of the type y is equal to mx plus c, the equation of a straight line, where y is a measured value of lattice parameter AM and x is cosine square theta. Therefore, if we plot AM against cosine square theta, the intercept on the y axis will be AC, which is the precise value of the lattice parameter, and AM will be equal to AC. You know, this has become M again, it is an error here. AM will become equal to AC when cosine square theta is equal to 0. Now, let us suppose the situation where we have got the diffraction pattern of a material, and this is one of the samples which we have already discussed in connection with the determination of crystal structure. Now, that material was the second sample which we studied, and it is a BCC sample, and if you will remember, the HKL values for the lines were 8 in number are 110, 200, 211, 220, 103, 222, 123, 400. So, these are the HKL values of the 8 lines which appear in the pattern, and this pattern was the same as for sample number 2 in the lecture on determination of crystal structure. Now, we also found out in that case that the measured value of the lattice parameter A m are given by these quantities. This is 3.107 from the first line, calculated from first line, 3.154 calculated from the second line, 3.161 calculated from the third line, etc., and 3.164 calculated from the highest angle 8th line. Now, we know the sin square theta values. We plotted the sin square theta values for the 8 lines also. From there, we can immediately find out what are the corresponding cosine square theta values. So, here we have got 2 tables. This table, which gives us the values of the measured lattice parameters from the different lines in the X-ray diffraction pattern, and these are the corresponding cosine square theta values for the different lines. I had mentioned in connection with the previous lecture that the most precise value of the lattice parameter can be taken as 3.164 angstrom, because this was calculated from the highest angle line. Now, we will see how, using certain procedure, we can come to the most correct value of the lattice parameter. So, now we have 2 tables, one for the cosine square theta values and other for the measured values of lattice parameter from the 8 different lines. So, as per the procedure described earlier, we are going to plot these values. So, we plot the A m values, that means the measured lattice parameter values, along the y axis, and the cosine square theta values along the x axis. So, for any particular line in the pattern, we find out what is the cosine square theta value and what is the A m value, and plot a point. Similarly, for another line, we find out what is the cosine square theta value and what is the value of the measured lattice parameter. So, in this way, for all the 8 lines, 1, 2, 3, 4, 5, 6, 7, 8, for all the 8 lines in the pattern, we plot A m versus cosine square theta in this form. Now, what will be the next step? You see, the points are widely dispersed. Now, in order to determine the lattice parameter precisely, we must draw the best fit line through the experimental points in the plot just obtained, and then extrapolate that line to the point where cosine square theta is equal to 0, because under that condition only the measured value and the correct value of the lattice parameter A c will be the same. Now, how to put a best fit line through the experimental points, that is the question now. Now, we use a mathematical method here for this purpose, and that is known as the method of least squares. The essentials of this method are described here. Let the coordinates of a point x, y in the plot be related by the equation y is equal to a plus bx. To find the best fit straight line through all the x, y points in the plot, we must find out the values of these unknown quantities a and b in equation 15. Now, from equation 15 we can see that the value of y corresponding to x equal to x1 will be a plus bx1. So, the value of y corresponding to a point where x is x1 will be equal to, from this equation, a plus bx1. If the experimental value of y corresponding to that point is y1, then what will be the error in measuring the point x1 y1? The error E1 will simply be equal to y minus y1, and y is a plus bx1 minus y1. So, if we have a point x1 say, and if we find out that the measured value of y for x1 is y1, although the measured value should have been simply y, then the error that is committed in the measurement E1 can be written as y minus y1, and y is a plus bx1 for that particular x1 minus y1. Therefore, if we find out the sum of the squares of the errors in all the experimental points, then you can write down summation E square will be equal to a plus bx1 minus y1 square for the point x1 y1 plus a plus bx2 minus y2 square plus the term for the third, fourth, fifth, sixth and 7 and 8. So, there are 8 lines. So, we will have 8 such quantities. The theory of least squares states that the best fit straight line is the one which makes the sum of the squared errors a minimum. Thus, the best fit, best value of A is found out by differentiating equation 16 with respect to A and then equating the result to 0. So, we write d sigma E square dA, and from these 8 quantities we can write it down as twice a plus bx1 minus y1 plus twice a plus bx2 minus y2 etc., etc. must be equal to 0, which means delta or sigma A versus b sigma x minus sigma y will be equal to 0. In a similar manner, the best value of b can also be found out by differentiating E square with respect to b, and if we find out the values, we will see that a sigma x plus b sigma x square minus sigma x y should be equal to 0. So, these are the conditions to be fulfilled in order that the error is minimum from all the points. Now, these equations 17 and 18 are known as the normal equations. So, rearranging the terms in the equations 17 and 18, we get sigma y is equal to sigma A plus b sigma x, and then sigma x y is equal to a sigma x plus b sigma x square. we will now demonstrate the use of the method of least squares to find out the best fit line for our problem. Now, in the equation A y is equal to a plus bx, y represents the measured lattice parameter values a m, x stands for cosine square theta values for all the lines in the pattern. Let us substitute the data for a m and cosine square theta in equation 19, which is of this form. Okay. So, let us substitute the values of the data for a m and cosine square theta in this particular equation. Adding all the expressions, we get the equation 25.192 is equal to 8a plus 3.702b. In a similar manner, let us substitute the same data in equation 20, which is of the form sigma xy is equal to a sigma x plus b sigma x square. Adding all the expressions here, we get the equation 11.632 is equal to 3.702a plus 2.303b. Now, solving equation 21 and 22, we get a is equal to 3.160, b is equal to minus 0.023. Therefore, the equation for the best fit line is y is equal to 3.160 minus 0.023 x. Now, here the calculations for the equation sigma y is equal to sigma a plus b sigma x are shown, where for the 8 different diffraction lines in the pattern, we have put the values of cosine square theta and a m at appropriate places, and that gives us this equation which we have already mentioned. In a similar manner, we have also put the appropriate values of a m and cosine square theta in this equation sigma xy is equal to a sigma x plus b sigma x square, and when we put those values, we get this kind of an equation which we have already used in order to find out the values of a and b. Now, let us take two different values of x, say, namely 0.1 and 1.0. Now, if we substitute these values in the equation 23, which is given by y is equal to 3.160 minus 0.023 x, we get y is equal to 3.158 and y is equal to 3.137 respectively. So, for x 0.1, the y is having this value, for x equal to 1, y has got this value. Now, we plot these 2 points and get a straight line and extrapolate it to the y axis. So, by doing so, this is the best fit line passing through the 8 points, and this is the point which will give us the value of the lattice parameter very, very accurately, because here cosine square theta has got a value 0. So, this is how the most precise lattice parameter can be obtained if we are given a set of measured lattice parameter values and the corresponding cosine square theta values. So, this is about the Debye-Scherrer method, in which we can find out the lattice parameter or parameters very, very accurately. Now, when you go to the more modern diffractometer method, the errors are sometimes quite different. Now, the most important sources of error in the measurement of D and therefore A using the diffractometer are the following. One is misalignment of the instrument. Number 2, using a flat sample instead of a specimen which is carved to conform to the focusing circle. The third source of error is the absorption of X-rays by the specimen. The fourth source of error is the displacement of the specimen from the diffractometer axis, and the fifth source of error is the vertical divergence of the incident X-ray beam. Now, there are relevant extrapolation methods for correcting the values of D and A, but you see these errors in this particular case vary in a complicated way with theta. As a result, no simple extrapolation function can be used to obtain high accuracy. A fairly accurate value of the lattice parameter can be obtained by simple extrapolation against cosine square theta, as we did in case of the Debye-Scherrer method. Sometimes extrapolation of the measured lattice parameter can also be made against this function cosine square theta by sin theta plus cosine square theta by theta. This relationship holds quite accurately down to very low values of theta and not just at high angles.